Last time I asked you to come up with a single funniest ever statement that would relate 4 words: late, elate, plate and slate. Anybody? Anybody? Sir, I'm late because? No? How about Thursday? Can I get some input from you guys? Thursday, a single statement that works as an excuse for you. You're late because, and you're going to be using all these 3 words: elate, plate and slate. Let's see. Try to tickle my funny bone. Alright, so let's get started. Bored with orthographic views already? Are you? Huh? Yes? Third angle, first angle, 3 views, FTP, front, top, profile. Want to learn something new? Yes? No? Maybe? Alright. So we'll talk about axonometric views, and in particular we'll talk about isometric views. You've done this exercise before. Okay. What did we do? We took this solid and we drew the orthographic views in the third angle projection. Right? What if I don't give you this object? What if Mr. Ashish, can you come up? Yeah. And Vasu is there. So what if Ashish gives Vasu these 3 drawings and asks Vasu to interpret these drawings? Would it be difficult or would it be easy? Not that easy. So would you need this drawing or would you not need this drawing?
Each object has a unique representation, so we can actually get the object back in the like, I don't know how to do that.
You don't know? Okay. All right. So the question is, given the 3 orthographic views and nothing else, is it possible, is it feasible for you to interpret the object? Who would say yes? Who would say no? Anybody who says yes? Would it be difficult? Yes or no? It would be difficult. But if I show this object to you, you will be like, fine, you have an idea of what an object would look like in 3D, okay, and you also have an idea as to what the object would look like when looked at from 3 different directions, 3 different orthogonal directions. Okay? So would you say that this picture is complete? The 3 orthographic views and a pictorial view or a 3D view? Would you say that? Yes or no? Okay. Another example. What if I don't give you this? Even more difficult? Yeah? But if I give you this, then you have a fairly good picture of what an object would look like. Third example. If I don't give you this, things might be a little difficult for you to interpret, but if I give you this, you're fine. Okay? You know what these are? Orthographic views. What is this? What is that? This is what we are going to be learning today, isometric views. To draw a single, so to speak, 3-dimensional picture of the object. And I plan to bore you guys today with a lot of math. Well, if not a lot, then a little bit. So let me read what's written there. Through multi-view orthographic projections, we observed how the object looked when parallel projections were taken on 3 mutually perpendicular planes. Okay, and down below, in axonometric projection, the object is oriented, read as rotated twice, a priori and appropriately, so that all its three-dimensional features are clearly visible on the vertical plane of projection. Okay? An example. This is a chalk box. Okay? What do you see? What do you see? A rectangle? So, what I am saying back there is, if I rotate this object once and rotate this object the second time, okay. So, when I rotate this object once, how many planes are visible to you? 2. And then when I rotate this object the second time, 3. Yeah. So, you see plane 1, plane 2 and plane 3, and you also see that there is a pothole in this chalk box and a few chalks. Okay. So, the entire trick in trying to get the three-dimensional picture of this object is to rotate this once, rotate this twice, so that all the 3 dimensions of this object are visible to you. Okay. So, we will try to learn the math behind this. Let us say we have a unit cube. How many edges? Cube, 12, lengths, all of them 1. Okay. What you see is the vertical plane of this cube, and let us call that plane as the xz plane. One of the vertices of the cube is at the origin of the axis. This is the x, this is the z, where is y? Outside or inside? Inside. Right hand rule. Okay. Let us practice. Let us orient this cube in such a way that you are able to see the 3 planes. Right now you are seeing just the 1 plane. Let us first rotate this cube about the z axis by an angle alpha. When I do that, I see 2 planes, right? Fine. I am calling this x projected, okay, but it is essentially containing the projected length of this edge and also the projected length of this edge, right? But the actual reference frame happens to stay stationary, it is fixed, okay. And then, so you would actually see 2 of these vertices, PP and QP. At first you are seeing only this vertex, right now you are seeing 2 planes. And then, by the way, let me ask you this. Let me go back, rotate. So, this length is 1, right? Okay. When I rotate, what happens to the length? Does it get decreased or increased? By what amount? Good. Okay, decreased by cos alpha or decreases to cos alpha? 2 cos alpha. Okay. Now we rotate the object about the x axis. Okay. When we do that, rotation angle beta, we get to see the 3rd face of the cube. Okay. Right? Okay, forget don't worry about that. And then you also see 3 vertices very distinctly, PP, QP and RP. Okay. Would you agree with this? Are three-dimensional features of the cube visible to you? Yes? Starting with a single plane to two planes to now three planes? Yeah? Yes or no? Okay. What is happening to these three lengths of the unit cube? When you perform one single rotation, you set the length reduced to cosine of alpha. Okay? In this case, what? Any idea? No idea? We need mathematics for this, na? But would you say that these lengths are equal to 1 or less than 1 or greater than 1, all three of them? All three of them less than 1. Fine. Huh? Yes or no? Who says no? Yeah, why do you say no? Z component is not changed. Is this true length? Is this true length? Yes? It's totally vertical. Now, if I rotate it towards myself, what happens to the length? Decreases by how much? By cosine of this angle, huh? Cosine of this angle. Okay, so all lengths will change, and it so happens that all lengths will get reduced. Okay? Now, depending on what angle alpha is and what angle beta is, we'll have to figure out by how much do these lengths actually get reduced. For that, we need mathematics. You would agree with this, no? All lengths are different for arbitrary angles alpha and beta. Now, it so happens that for a certain set of angles alpha and beta, you get these three lengths to be totally equal. And when you're looking at that projection, it's called the isometric. Iso means same, metric means scale, isometric projection. When all the three lengths are equal. Okay? When two of these lengths are equal, it's called dimetric projection. Di, two, metric, size. And when none of these lengths are equal, it's called a trimetric projection. Okay? You guys are getting bored already. I see so many yawns. So this is something that you would need to keep in mind, but in particular, we are going to be looking at isometric projections as a part of this course. So you have a plane, xy. You have a particle or a point, which is at fixed length with respect to the origin. Okay? So this length is fixed. So you can consider this to be an edge, and you're going to be rotating this edge about the axis that comes to you, okay, by some angle. So the coordinates of that point are xj and yj, the original coordinates. The new coordinates are xj star and yj star. The initial angle made by this edge OPJ is alpha. OPJ is of length L. Okay. This edge is being rotated about this axis, the axis that comes to you, by an angle theta, right? Have you come across this before? Yes or no? Yes? Straightforward? So this projection, this horizontal projection is xj, the x coordinate of pj. This vertical projection is yj, the y coordinate. This horizontal projection is xj star, this is yj star. Okay? Given the angles theta and alpha, can you relate these projections? You can. Xj star is L times cosine of theta plus alpha, which is, if you expand, that is L cosine of alpha cosine of theta minus L sine of alpha sine of theta. L cosine of alpha is xj, L sine of alpha is yj. So xj star is xj cosine of theta minus yj sine of theta. Okay? Likewise, you can find yj star as L times sine of theta plus alpha at the end, that is xj sine of theta plus yj cosine of theta. Okay? And in matrix form, you can write xj star yj star equals cosine of theta minus sine of theta cosine of theta times xj yj. That is something that I think you may have come across before. You have? Okay. So far so good. So this matrix is called the rotation matrix. Okay? Cosine of theta minus sine of theta cosine of theta. What happens to the z coordinate of the point? If this is the x axis, this is the y axis, what happens to the z coordinate of the point? Remains same or different? Same. Okay. Coming back to the cube, one of the vertices is called O, let's say. Okay. This vertex is P with coordinates 1, 0, 0. Q is inside the screen with coordinates 0, 1, 0. So y axis is pointing inwards and R is 0, 0, 1. Okay. We are going to be applying the result, the rotational result on this. Rotation about the z axis. If you look at this block, this 2 by 2 block, that would rotate your x and y components. Okay, and your z component remains the same. So you have 0, 0, 1 here and 0, 0, 1 here. Okay. So the old value of x coordinate, the old value of y coordinate, the old value of z coordinate pre-multiplied by this matrix will give you the new value of the x, y and z. Okay? All right? Everybody with me? Yes, no? Good. What if I want to now find rotation about the x axis? What is the entry here? 1. Cos. Is it too trivial? No? Anyhow. Got it right? So remember, let's not lose the physics. Let's come back. A single plane, rotation about z by some angle. Okay? That rotation matrix is given by R of z. And then this is my x axis, rotation about the x axis. The second matrix gives you the rotation. Okay? And the third step is whatever you see here, you have to project that on the vertical plane. Okay? What happened then? Your vertical plane is what? XZ plane. Okay? Your vertical plane, your screen plane is the XZ plane. Right? So your x coordinate will remain the same. Your z coordinate will remain the same. What will happen to your y coordinate? 0. So this is your projection matrix. Okay? Yes or no? No? Step 1, step 2. Okay? Whatever the x, y, z coordinates are. This is my xz plane. Okay? This is my xz plane where y coordinate is 0. Okay? If I project this guy over here, x and z coordinates from these two rotations and the y coordinate will be 0. Fine? Now, this is the tricky part. When you perform transformations, you have to follow a certain order. Okay? First, you are performing rotation about the z. Second, you are performing rotation about the x. And third, you are projecting. Okay? When you follow this order, rotation about z, then about x, and then projection of the yz plane, you'll have to pre-multiply matrices. Okay? The first matrix On the right is rotation about z, then rotation about x, and then projection on the yz plane. And when you multiply all these three matrices, you will get the result on the right hand side. Top row cosine of alpha minus sine of alpha 0, middle row 0, 0, 0, which explains that you have actually gotten the image of the object on the xz plane, and therefore all the y coordinates are 0. And the third row, sine of alpha, sine of beta, cosine of alpha, sine of beta, and cosine of beta. Okay? Little bit of math would be boring. What do you have to say about this? These are the coordinates of what? Huh? These are the coordinates of P. Okay? These are the coordinates of Q, and these guys are the coordinates of R. Right? If I want, or if I ask you what the new length of OP is, what would you have to say? New length of OP? Huh? X squared plus y squared plus z squared cosine alpha squared plus sine alpha squared times sine beta squared. Okay? All right? New length of OQ, square this up, square this up. And new length of OR, right? Enough of math? A little more. Axonometric projections, you have three categories: isometric, dimetric, and trimetric. What happens in isometric? All three lengths are equal. What happens in dimetric? Two lengths are equal. Trimetric? All lengths are different. If I want to work with the isometric case, I have to equate or have to ensure that OP is the same as OQ and that's the same as OR. Okay? How many equations? 2, 3, 2. How many unknowns? So if I say that OP equals OQ and OR equals OP, I should be able to solve for alpha and beta. How many solutions do you expect? Huh? Would you expect a unique solution? Would you expect more than one solutions? If so, how many? More than one? If you do the algebra, which you can in your hostel rooms, okay, you will see that beta comes out to be plus minus 35.26 degrees and alpha comes out to be plus minus 45 degrees. So in fact, you have 4 solutions. Okay? In fact, you have 4 solutions. Right? Okay? So you have positive rotation and correspondingly you have negative rotation in both directions for alpha and beta. Enough of math. So this is the crux, but in TA 101 we don't worry about the intermediate steps, we only worry about the final result, and this is what the final result is. That if you incorporate those angles alpha and beta, okay, what it essentially means in terms of drawing is you get to know the orientation of the x axis, the y axis and the z axis of the object, of the cube. Okay? The x axis is oriented at 30 degrees from the horizontal. The y axis is also oriented at 30 degrees from the horizontal and the z axis remains vertical. Lunch followed by mathematics is not a good combination. Okay? So, in your labs or when drawing isometric views, do not worry about the math, you can just start from here. Pick a point on your sheet, draw x-axis at 30 degrees from the horizontal, draw y-axis at 30 degrees from the horizontal, draw the z-axis, which remains vertical. Okay? Once you have identified the 3 axes, okay, you should be able to draw the 3-dimensional picture of the object. And we will see one example. Yeah? Louder. Plus minus 35 or 30. Okay. In what range? Yeah. Yeah. There should be 4 values. Corresponding to those values, you will probably figure that you will get one of the axes as this, no matter what. Okay? You will get the other axis as this, no matter what. And your z-axis will remain vertical, no matter what. You can try it out. Okay? All right. So, it could be as well 35.26, there would be something else after 6. So, in that sense maybe it is an approximation, but cosine of beta is under root of 2 by 3, that is the precise. No, this is exact. How did we get that? You see this result? Okay. Better? Let's focus on the p coordinates. Okay? P coordinates are given by cosine of alpha 0, cosine of alpha 0 and sine of alpha. Thank you. Huh? This guy, right? Let's just focus on P. Okay? So if you plug in the value of alpha, what do you get? Let's just take the positive values for now. What is cosine of alpha? 1 by root 2. Y is 0. What is sine of alpha? What is sine of alpha times sine of beta? So this would be 1 by root 6, na? Fine? Fine? All right. So my point P will be here somewhere. Okay? Remember that this is the xz plane. The vertical plane is the xz plane. Okay? My point P will be here somewhere. What is the x coordinate of that? 1 by, what is the z coordinate of that? Okay, so what is the cosine of the angle? What's the cosine of the angle? Which is what? 30 degrees? Huh? Okay, that's how you get it. And likewise, if you consider Q, you will get 30 degrees on the other side. Right? Okay? All right, so the lens get shortened or foreshortened by, yeah? How have you got the what? Last part of what? Step 1, rotation about x, rotation about z, then rotation about x, and then projection on the xz plane. So the screen plane is the xz plane. Okay? So you are actually seeing all three-dimensional pictures of an object on a vertical plane, which is the xz plane. Fine? Fine? Do you agree with the math? Okay? If you plug in the values of alpha and beta, let's take just the positive values. Okay? You will get the new coordinates of p as 1 over root 2, 0 and 1 over root 6. New coordinates of q as minus 1 over root 2, 0 and 1 over root 6. New coordinates of r as 0, 0 and root 2 over root 3. So your p will be lying here. Your q will be lying here. Right? And your r will be lying here. Okay? But this is what? X coordinate of p, z coordinate of p. Okay? So the x coordinate is 1 over root 2. The z coordinate is 1 over root 6. This is 1 over root 2. This is 1 over root 6. Okay? So this, yeah, so this over this is what? Tan of this angle, which is what? Which is what? You can work out the same for q. Okay? So the x coordinate is minus 1 over root 2. The z coordinate is 1 over root 6. Tan of minus 1 over root 3, which is 30 degrees on the other side. Okay? All right. What happens to lengths? They get shortened, they get foreshortened. By what factor? Or to what factor? Huh? How? So OR, folks, can I have all ears here? So the initial length of OR was 1. The final length of OR is root 2 over root 3. Okay, so OR has shortened by root 2 over root 3. Okay, and so has OP and so has OQ. Right? Okay. So the lengths in all three dimensions, they have shortened by equal amount, which is root 2 over root 3. So this is something for you to understand. Okay. So through this lecture, you can understand the math, but the take home message is this part. When you start drawing your isometric views, pick a point on your sheet, draw the x-axis at 30 degrees to the horizontal, draw the y-axis at 30 degrees to the horizontal, draw the x-axis, draw the z-axis vertically upwards. Message 1. Message 2, that your true lengths, they need to be factored, they need to be multiplied by root 2 over root 3 to get the isometric lengths. Okay? And we are going to be working on how to draw the isometric scale. Horizontal, you have a line, you have another line. This line is at 45 degrees. This line is at 30 degrees. Mark the true lengths on your 45 degree line. True lengths on the 45 degree line. If you take the horizontal projection of, let's say, length L, which is the true length on the 45 degree line, then the horizontal projection will be L times cosine of 45. Okay? What is this length? This length over this length is cosine of 30. So you can find what that length is. L cosine 45 over cosine of 30, which is L times root 2 over 3. So in effect, what's happening is that you are scaling the lengths on the 45-degree line by root 2 over root 3. If you are taking vertical projections of those points on the 45-degree line on this red line. Okay? Mark these points, draw verticals on the red line from the green line. So, this is the true scale, this is the true scale, and this is the isometric scale. Okay? So, this is the second take home message from today's lecture. Okay? As far as TA 101 is concerned, you don't need to worry about the math that we have done. What you need to worry about is how to draw the x, y and z axis on your sheet and how to come up with the isometric scaling. Okay? So, in your lab assignments and homework assignments, when I say isometric drawing, I want you guys to draw with isometric scale, with the scale. Okay? When I say isometric view or isometric sketch, I would want you guys to draw isometric view but with true scale. Okay? Okay? So, keep this in mind. So, let us draw the isometric view from these three orthographic views given. Third angle, first angle? Third angle? How do you say that? Third quadrant? Fine. How do you think, or what do you think the object is going to look like? How do you think the object is going to look like in 3 dimensions? Let us get back to our exercise. First thing, get one of the axes, the x axis. Now, realize how I am drawing the axis. Okay, I am drawing the axis opening towards you, not opening away from you. X axis, y axis and the z axis. First thing, both x and y 30 degrees from the horizontal, z axis vertical. I know the dimensions from the orthographic views. I can draw the bounding box. I can draw the bounding box. Okay? Yeah? The bounding box. 3-dimensional bounding box. Which plane is this plane? Which plane is this plane? Huh? X axis, z axis, this is y axis. So, this plane here is the YZ plane. Okay. How about this plane? XZ. XZ or XZ. Okay. So, the trick in drawing isometric views is to identify 3 different planes distinctly and work on these planes. Okay. From now on, I will not utter a word. I will just have you see what is going on.